Okay everyone, this is going to be a video to find the moment of inertia for a thin rod or a stick about its center. And it's kind of late and I'm just doing this off the top of my head. Usually I'll prepare some things in advance, and so pardon me if I stumble here or there, but I think I can remember how to do this. So we have this stick, and we want to turn the stick about a point through its center, just like this. We want to find what's the moment of inertia of it through its center. So let me remind you of some definitions that we've had already. First of all, we have I, that's moment of inertia. Let's maybe do a different color. That one doesn't seem to be showing up that well. That's a little bit better. And so if it's for just objects, we have the sum of MIRI squared. So that would be if you just had a mass over here and a mass over here, and you were rotating it about some point like this. You would take this one, that mass, times this radius, and you would take this mass times this radius, and you'd add them together. And that's assuming that this stick is massless or has very little mass compared to these two. So the other formula that we had when you had a solid distribution was the integral of r squared dm. And that's what we want to work with this time. So we're going to have a continuous distribution of mass. In case you didn't watch the video that I had done in the past about center of mass and that integral, I want to just remind you how this is going to work in terms of density. So if you watched that part already, great, you can see it again. If not, then this is important. So there's actually a couple different ways that we can think about density. Generally, you know density as mass per volume, and this is going to be called a volume density. And there's actually going to be a couple of different densities. So there's a volume density, mass per volume, and we use the Greek letter rho for that. And then that is going to be, you could just call it mass per volume. So that's just generally how you think about the density of something. I don't know what I have here, glue stick. That's a bad example because that's non-uniform. All right, so this is a solid object and it's got 3 dimensions. So we would say it has a volume density. We could also do a different kind of density, and we could have an area density. That's going to be a mass per area, which is strange to think about. That is going to be a sigma. That's the symbol for that. That's mass per area. So if you had something that was 2-dimensional, say for example like a piece of paper, it's not quite 2-dimensional, but close enough to 2-dimensional. So it's got a length and a width, but it doesn't have any depth to it. You could call it, have an area density. So that's its mass divided by its area, whatever length times height you want to do for this area. And then the kind of density that we want to do for our thin rod or stick is we want to do a linear density, or line density, which is going to be mass per length. We abbreviate that as lambda, and that's going to be mass per length. So when I had this chopstick out here before, we're going to imagine that the height of the chopstick and the depth of the chopstick are insignificant compared to the length of the chopstick. So we're going to call this more or less a one-dimensional object. So, you know, physics does this sometimes. What does it mean to be very small? So it's very thin in this direction and very thin in the up and down direction. What does very thin mean? Well, I don't know. It's up to you. Less than 10% of its length would be its width and its depth. So just much longer and not that thick. And that just allows us to do an easier calculation, a linear density calculation, so mass per length. Let me also remind you that if you take an object and you break it into a smaller piece, that the density actually doesn't change. So if I took this chopstick and chopped it in half or chopped it into a small piece, all the pieces are going to have the same density, as long as it's a uniform density. That's why the glue stick wasn't such a good idea, because it's not uniform density. Obviously, it's got lots of different stuff. So if it's uniform density, then it doesn't matter what the size of the piece of object is, which means that for a volume density, we could call this actually dm dv. For an area density, we could call it dm dA. And for linear density, we could call it dm dL or dm dx, really is how it's going to turn out for us in a minute. So that's that. So let's define a couple of things here for our thin rod. So we're just going to have something, there's our thin rod, and it's going to have a mass of m. It's going to have a length of L, like that. And then our axis is going to be right in the middle. There's our axis of rotation. And the trick here is that we have this integral of r squared dm, and we have to get the r squared and the dm to kind of talk to each other. That's where we're going to go back here and do this linear density formula. So first I'm going to just make a variable change. Since I don't really have a radius here, it's more like a length. Well, actually, let's talk about this first. So what we're talking about is a tiny little piece of mass right there. So we're just going to break off a tiny little chunk of mass, right? It's going to have a little bit of dm to it, and it's going to be located at a distance. I'm going to call it x instead of r. So x is the distance from the axis of rotation over to where my mass is. So that's going to change this one, just for a variable change, into x squared dm. And then I also want to note that my little bit of mass here has a little tiny bit of width. So just this little bit of width right there is going to be a little bit of dx, meaning a tiny little bit of width and a tiny little bit of mass, right? So if we remember what our volume was, volume is going to be mass per length, but that's also going to be dm dx, which is very helpful for us because now you can see how I can get the dm and the dx to talk to each other. Sorry, this is getting a little bit crooked. There we go. So I get the dm and the dx to talk to each other just like this. So let's just rearrange this to dm equals. So I'm just going to pull this dx over to the other side. So I'm going to get dm equals m times dx over L. Or maybe I could write it as m over L dx. So now I have something that relates dm and dx together just from the volume. Sometimes you'll see this, oh, I already did that, written as lambda for linear density. So now this really helps us out because now for this integral over here, I'm just going to write it down over here. Now I can have integral x squared, and then the dm turns into this thing over here, m over L dx, right? So that works out pretty well. M over L doesn't change, that's a constant, so then I can turn this into m over L integral x squared dx. So this is turning out to be a pretty doable integral for us. The trick now is we got to find some limits of integration before we can really do the integral, so it's going to be a definite integral. So where are we going to go from? If this is our 0 point right here, we're going to go in the positive direction up to an x value of L over 2, and then in our negative direction we're going to go to a value of negative L over 2. So when we look for our limits of integration, we're going to go from negative L over 2 up to L over 2. So that's pretty doable there. And then this integral is so easy. So I'm just going to wrap it around down here one more time. So we're going to get m over L, and then when I integrate that x squared, I'm going to get x cubed over 3. And we're going to evaluate that from minus L over 2 to positive L over 2. So that's going to be m over L times, so let's see, I've got L, let's bring the 3 up, bring that third out. So now I've got L over 2 cubed, so that is going to be L cubed over 8 minus this one down here, negative L cubed over 8, which is really just going to turn that into a plus. Oops. Finish that bracket off. That turns into a plus. Just come around over here. So that's going to be m over 3L. And then I've got now, this is going to be inside the brackets, L cubed over 8 plus L cubed over 8 is going to give me L cubed over 4. So bringing all these together, I can cancel 1L, and then I have this 12 on the bottom. So what we really get is ml squared over 12, or sometimes written as 1/12 ml squared. So that's what the moment of inertia is. This is I. The moment of inertia for a thin rod about its center is 1/12 ml squared, right? 1/12 ml squared. That's the moment of inertia. So it only matters what the length is and what the mass is, not the height this way and not the depth this way, right? So that's something important to realize. I'm going to look my notes real quick because I thought I was going to do something else. So sorry if that cut out for you. There was something else I thought I wanted to talk to you all about. Oh, yes. So let me just do this here. Let's see. Is it back? Okay, good. I don't know if I went away or not, but so now I'm back. I wanted to talk to you about something called the parallel axis theorem. Parallel axis theorem. So what this does is this allows you to shift your axis to somewhere else if you know the axis through one point, usually the center of mass. Let's go back to our stick. If our center of mass is right there, remember that's center of mass. And if we know that the moment of inertia through the center of the mass for the stick is 1/12 ml squared, we can find the moment of inertia through any other axis as long as it's parallel to this axis. So remember, we are going to spin our stick about the center point in this direction like this. So instead of going through the center point, I could go through a different axis, say like right there. So if I wanted to make that my axis of rotation like that, and have it, kind of get my hand out of the way, have this point be the center, just like that. So I can very quickly find a moment of inertia through a parallel axis, through this thing called the parallel axis theorem. So how it looks is like this. Here's my new axis. Let me draw it on here, maybe in a different color. So this is going to be my new axis of rotation, as long as they're parallel to it. And then it's got to be a certain distance away over here. For some reason, I don't know why the physics people did this, but they defined the distance between the center of mass and the new axis to have this letter h. I don't know why they didn't leave it as an x or something like that. It's really silly because it usually means height for h, so I'm not sure why they did that. So the parallel axis theorem says that the moment of inertia through this new axis is the moment of inertia through the center of mass plus m times h squared. So if you know this distance h and you know what the mass of this thing is, you can find the moment of inertia through another axis. And an example of this, and I think they asked this in one of the homework problems that I assigned, I hope they did, is let's say that this was a meter stick, 1 meter, and we treat it as a thin rod. If you know the axis through the center point, if you have an axis through the center point, you can find the I through the center of mass right here. And let's say you wanted to do that at like the 70 centimeter mark or something like that. You wanted to find this is your new axis of rotation. So then your h value here would be 20 centimeters. Probably better to write it as 0.2 meters, right? You can just plug that in here for your h, square that times m, add it to this new center of mass, and then you can see that that's that. It also means that because this is always going to be adding something in, your moment of inertia through your center of mass is always going to be the lowest value for your moment of inertia. So if I change my axis to right there, it's going to have a higher moment of inertia compared to that spot right there. And if I put my axis way over on the edge, that's going to have the highest moment of inertia possible for this thing. I guess unless I move the center axis way over here, which is possible, right? So how do I rotate it through this as my axis, right? So that's possible. But the center of mass is going to have the least moment of inertia. Great, so there are other things we can do, by the way, with this finding moments of inertia. And I had alluded to this before, but I'll have you try it out on your own someday, sometime. And that's finding it, say, for a disk. And you're going to use an area density for this one, and finding it through the center of the disk as it rotates like this. So how would you do that? I'll just talk about it briefly. But you want to find a little bit of mass somewhere. And it wouldn't really make so much sense if my little bit of mass was just like a little chunk of mass like that. What I really need, because it's hard to integrate that, because I have this one, and then I've got a little chunk of mass over here that have a different radius, and I've got a little chunk of mass here that have a different radius, and this little chunk of mass has a different radius, so that's going to be a little bit tricky. Instead, what we're going to want to do is we're going to want to set up our little chunks of mass to be concentric circles. So probably better to do it like this. So I'm going to have my little bit of dm be like that, a little tiny circle, a little infinitesimally thin circle just like this. And that is located at a distance r away. Of course, it has a thickness of dr between there and there. It has a dr. Yeah, so we can get this surface density as mass per area. Of course, the area of the whole thing, the area is going to be, if I make this radius r, so that's going to be pi r squared. But I can also express this as a dm. Oh, this is the tricky thing, now I remember. So how do I find the area of this little bit right here? This is sort of a funny little thing. So it's not that the area of this thing is just dr, because that only gets me this. So how do I find the area of this thing right here? It's actually going to be something a little bit strange. So this is going to turn into dm, and this is going to be 2 pi r dr down there. So it's like the circumference of this thing times the little bit of area that's inside of there. Sorry if that's kind of going off the screen for you all. So this is how I would set this one up. I guess I'll just show you since I'm here and we're here. So this r squared dm is now going to turn into integral of, let's see, so doing all that together, so dm is going to be m over a times 2 pi r dr. So this is going to be m over a. I can substitute that in, and it's going to be r squared times 2 pi r dr. So I'll bring the 2 pi out. 2 pi m over a integral of r cubed dr. And then you could substitute this a on the bottom here for this if you want to stick that down there. So and then we would want to integrate from 0 to r like that. So that's not such a hard integral to do, so you can try it out and see what you get. The end result of this, just try it out, do the integral out. We should be getting for a disk that the I is 1/2 m r squared. You can see that this pi is going to cancel with that pi, so the pi is going to be gone. This is going to be an r cubed, an r squared down here, and that's going to cancel with some of the r to the 4th powers. And anyways, it'll work out for you. So try that one out. And then if you really want to extend yourself, try this as a sphere. And then you've got a little tiny spherical shell inside of here that's got a little bit of dm for this, and it's located at a distance r. And how would you express a little bit of volume, this little tiny spherical shell inside there? So I think you work on that kind of stuff in your calculus classes. Great. I think I did pretty well considering it's late and I didn't really practice this beforehand. So hopefully you got something out of that and try it out. Fun stuff.